Hello, everyone. This is lecture 24 of Advanced Drilling, PTRE 451545. We should proceed today with Module 4. Most likely, I will be extending the deadline of the homework either for next Wednesday, or next Friday. I don't want to do it next Friday because there is going to be too much on the grader at the end of the semester. He's still working on the drilling story. He owes you homework 4 and the part 1A of the project. And I told him to focus on the grading the other class because the other class had a midterm. So I was busy, he was busy with that, so we need to, ideally, I want to extend this homework until Wednesday, what is it, the 28th, the 30th. Okay. Reason being, that's gonna give you one more office hour, one more lecture available. But if you wait, I mean, it will be too late if you start doing it on Monday, for instance. It's very, very long. And if we have time today, I will show you some of the plots, how they should look like, and you will understand that it's going to be long.
As I meant, the homework 5, right?
Homework 5, yeah. And it's going to help you when you do basically part B of the project because they are the same thing, basically, or very similar. You are basically modeling the same thing, modeling the line that you see on the first circulation of part B of the project. Now, part B of the project is 8-hour simulation, but of course you can speed it up at different times. But it's also a very fragile scenario in the sense of the math window there is very narrow. It's like 11.25, 11.3 ppg to 13. I think that the frag gradient is 13. Fracture gradient at the case issue is 13. So it's slightly like 1 point something ppg, which is very narrow. And if you leave the case as is and you just speed it up on its own, it's going to lead to an underground blowout. Now, if you let your BHP increase a little bit too much, you get an underground blowout. If you let your BHP decrease a little bit too much, you get more kick. So it's going to be a very fragile case. You need to take care with it. And the strategy that you should follow, I think, is, or what I suggest, is that you progress a little bit and then you save. You progress, you save, you progress, you save, you progress, you save. Then you have a failure, you don't save, so you can come back to the next one. And maybe you want to save with different names because you don't want to override the same file. If you are, because if you have a failure, it's basically game over. And whatever you did, you lost. Okay, we saw that. Where we 74 slides, huh? We finished not here, not here. We saw some ugly equations last time, and you're gonna need them for your homework. And I suggested that you derive this kind of equations step by step. You are expected to know how to derive them. Okay, so and you know step by step how we got there. And I told you that this number 4 here, this number 4 is not this number 4. It's not this. So it's many steps involved in the process. And I want you to know how to do it. Basically, how you go from here Boyle's law to basically here. Now, we are seeing this equation, this actual equation with the root, square root, several times, 3 times actually. It's for 3 extremes. One is at the initial, when you have the bottom of the kick touching the bottom of the well. That means the SIDPP is at initial value, and the H above is at initial value, and the pit gain is at initial value, and the angular volumetric capacity is at initial value, etc., etc. Now, the second one is when the top of the kick is touching the casing shoe depth. Now, normally, SIDPP won't change, okay? But I make it as if it's changing in case it changes, okay? Theoretically, it shouldn't change, but you never know what fluid you are dealing with. So it might change. Ideally, it will be kept constant. And if it's gas, though, and there's a big density differential, it will change. So SIDPP value might change. The depth H above here changes with the depth of the casing shoe because now the top of the kick is at the casing shoe depth. The pit gain is the pit gain corresponding to the casing shoe depth. And the C angular is the angular point at that, the angular volumetric capacity at that point. So those green variables are the ones that might be changing as you move from one equation to another, but it's the same equation ultimately. Okay, and we said if we do have gas, the pressure of the gas would be basically, well, there would be gas pressure, but if you move from the top of the gas kick to the bottom of the gas kick, it might not change if the gas is weightless, right? But the gas itself, the kick has a pressure value, and it's given by this equation, and I think you understand. This is basically the right leg of the YouTube model. SICP DCSG on the top, plus 0.052 hydrostatic, raw mat up to the depth of the casing shoe. And the height of the gas would be this. This is just addition, basically, or subtraction. Then, when the top of the gas kick column reaches the choke, basically the surface, that's when the SICP is maximized. That's when the top of the gas kick is basically at the surface. And the value would be calculated using this equation. Same thing as before, same equation, just SIDPP at that point in time, pit gain at that point in time, it will be maximum. And the angular volumetric capacity at that point in time. Now, in the homework, I told you something like it's an isothermal process.
Yes.
Okay. What does that mean if it's isothermal process? Okay. In this equation, how does that translate to? You have T gas and T rock. They just cross out. Okay, you don't need to care about temperature. Okay, good. Don't worry about temperature at all. And at that point, P gas would be the SICP, and H gas would be, I guess, this. And you need to make sure, as good engineers, that the SICP max is less than the mass at that point. So probably at that point, you're going to have the choke as open as you will have it throughout the whole process. FPP is this is not V pit gain as a function of FPP, is V pit gain times FPP. I think in the homework it was like 6,600, something like that, and it stays the same, so it doesn't change. Doesn't value. A generalized version. We saw three equations, and they're basically the same equation. How do I take them all together and I generalize them? Now, I will take it and make it SICP at time t is equal to SIDPP at time t minus 0.052 rho mat h above at time t, SIDPP at time t plus all this. Basically, I make everything as a function of time. And of course, the temperature of the gas will be changing as you move up, but in isothermal cases, we don't care. We're assuming it remains as T rock, so it cancels out, makes it easy on you. Yep, there you go. I forgot I had it here. Different models of gas behavior, like non-ideal gas, which is the PV equals Z nRT, can be applied to derive similar expressions for the variation of SICP during the Driller's method first circulation. So highlight this, it's gonna be important. This is for Boyle's law. Boyle's law is for ideal gas, right? Okay, what if I have something else? I can derive an equation similar for non-ideal gas or real gas, as we call it, or anything, basically. If you give me the equation of state, and this is where I was telling you, don't look at that tab that says on the drilling simulator that guesses what kind of density of the kick has, etc., because this one, that tab assumes an equation of state. Okay, I don't, I put water, which is basically incompressible. It was assuming it's gas. So I was like, that's why I was telling you guys, don't look at that tab. Derivation of SICP during the weight-on-weight circulation is harder but positive. This is the equation that the drilling simulator is using, by the way. These are the equations that the drilling simulator is using. Now, how does that translate to gas kick? If the kick is gas, in the YouTube model. Okay, here we have what? It's the beginning of the circulation process, SIDPP at I initial, SICP at initial, all purple on the left leg, yellow at the bottom of the right leg, and then we're starting to move up. Look at that. We are at the point where the top of the gas kick is at the casing shoe depth. And now we have this equation. And we're dealing with this. Okay, and you know how to calculate it. This is where H above became DC. This is basically DCSG. I don't know why there is extra space there. I need to fix those slides. And now, that's when the SICP is maximized. And when you have the top of the kick at the surface, basically, at the choke. And you want to make sure that this is always below MASP. Okay?
A quick question. How do we determine the maps?
The
at
MASP?
the beginning, yes.
We gave you the equation, right?
Okay, yeah. I remember.
It's, well, provided that the casing shoe is the weakest point. Might not be, who knows? But you have to use it. In the homework, you have to use this. The second one, the easiest equation, not the EMW.
So that means
This one.
Pressure.
The fractional pressure at the casing shoe minus the fluid above it. Okay. What I was saying, I forgot. Oh yeah. No, I want to be here.
Yes.
I was showing you guys that this needs to be less than MASP and always bigger than the original SIDPPI, right? Should be bigger than that. Otherwise, I get a kick, right? And this one should also be bigger than the SIDPPI. Again, hypothetically, the
That should be SIC or initial with a SI. When you're talking about the casing pressure over there, certain casing pressure, why you are talking about SID initial?
because that's the point at which you basically get kick.
Okay.
SIDPP initial is what you are missing.
Yeah.
Is what you are missing, is the mat weight that you are missing for preventing a kick, basically. Now, hypothetically, these are going to be equal throughout the circulation. But, I mean, you know, in the real world, it won't be. So you need to make sure it stays like that. And then you start getting the kick out of the well. So it gets less and less. You see it flaring. You turn your up. If you turn the noise of the up, you're going to hear shh. That's because it's burning. The kick is burning, it's flaring. It's being flared. So SICP is dropping, and SIDPP might be dropping. And, you know, that's when you are burning the gas kick, okay? Okay. Any questions?
Yeah, I don't know if it's related. It's just a general question still about kick. If I'm drilling a formation that doesn't have any fluid,
Yeah.
and probably my mud density is not the correct one, will I have a kick since the formation doesn't have any fluid?
Well, there is no fluid to enter you're basically drilling through glass, something like that.
Sand.
Well, sand is likely going to have water in it.
Okay.
But you might drill through salt. Then you have other worries because your fluid from the well might want to go into the salt. So you need to make sure that you are going to be, you have a lower activity. You need to play with the activity values. Now, let's see. You may want to use oil-based mat or something, you know. But remember, water will flow from high activity to low activity region. We did that in the other class, the undergrad class. We had an exercise for that. Yeah, you because technically kick is the definition is fluid moving from the rock into the well, right? Okay, there is no fluid, but let's just say there is fluid, but the rock is very, very impermeable. It's basically glass. It's like shale. You have other worries there. Because if the mud has lower activity than the shale, water will want to move from the shale into basically the shale will be collapsing and falling into the rock. You have instability issues, etc., etc. You need to make sure that your activity is balanced. And that's why oil-based mats were invented. Activity controlled mats, whatever they call them, I forgot now, they are good up to a certain point. Even today, we did try some synthetic-based mats that were not oil-related. They were not oil-based because oil-based are expensive in the Permian. We tried some synthetic-based mats that were supposed to hold the shale from collapsing, and they were not good. Because you know when you are drilling now in Texas, you have it's not a little bit of shade that you are going to encounter. You're going to go horizontal and then you are shade all the way. Okay, so there, normally what they do, or what they did at my time, and they still do, they are switching to oil-based mat from water, and they keep like that until the end. And when you switch to oil-based mat, you're basically, it's more expensive. It's more expensive. You want to avoid that. So they are always playing around to find some synthetic base mats that would be cheap, and then you will not have the problems that you have with the, yeah, but we could see that it wasn't working. The samples coming out from the shell shaker were like huge. Like, you know, it wouldn't be working. You would understand that it wasn't working. Now, what they do normally is that they drill the whole vertical section without even cleaning the mat sometimes. Bypassing just recycling the mat. Bypassing the shell shakers, bypassing everything, goes directly into the mud pit and then back into the well. Or you just dump it. You can do that. But once you are in the shale, you need to bring oil-based mud, you need to bring tanks, etc., etc. And normally they rent this mud. They rent the oil-based mud. So they have to bring it back. And whatever you are missing amount, you have to pay for it. Okay? There is some portion that is like allowed. It's expected to lose some, even if you drill properly, you are gonna lose some money. So maybe there is a threshold volume that you are allowed to lose when you are using their mud from the company. But when you are, if you say you encounter a cave or something, a cavern, not cavern is too big, like a karst, if you are, it's common in carbonates, and you have loss of circulation, you buy mud, you buy that mud. You have to pay for it. So it's, yeah, there is a lot of incentive to move away from the oil-based mud. Even for health reasons, it's disgusting. It's disgusting. The crews get paid extra every day they work with oil-based mud. It's eventually you become allergic to it. Anyway, are you ready to watch a video for the circulation?
Good.
If there are no other questions, by the way. Why doesn't it open? Sign in to confirm you are not a robot. Why do we need to sign in? Anyway.
Hey, the browser is not your browser. Yeah.
So what do I do? Okay. But it's not really a.
Maybe you can just go to normal YouTube and then type your name and then maybe copy that and put a normal YouTube and then it will come.
Yeah, but it shouldn't be.
Yeah, I don't know, but you can go normal YouTube. Then now set your.
So I need to sign in.
That is why I say that's what. Yeah.
Sign in to continue to YouTube. I don't have a Google account for that.
Okay. But why are they asking? But can you just type normal YouTube somewhere like you're going?
Oh, okay. Yeah.
Yeah.
Yeah. YouTube, well, video sharing company. YouTube. Try searching to get started. Okay. Drilling simulator. Free drillers method. Okay. This is the one.
Yeah.
Uh,
What's happening?
yeah.
Or you can click on sign in. Let's see.
It's gonna take me to.
You don't have a Gmail attached to it?
Yeah, it doesn't have a
I
Gmail.
have, but it's not attached to the YouTube channel. I think.
Perhaps someone log you out.
Who log?
Huh?
Someone may have logged you out.
No, but it's supposed to be able to.
He said he doesn't have this in account. And I don't know, maybe Gmail just want you to use your
So
Gmail.
Yeah, but then I have to log in every time. I don't remember if the password is correct.
Correct or not, yes.
Phone number, it says.
Yeah, so that you get some code.
Find your email. Enter. No, I don't want. I think I put the. Okay, next. Oh, now he wants the password.
Yeah.
I don't know if the YouTube channel is tied to this Google thing. Check your phone.
Oh,
Confirm. Okay, I can confirm that. It's not a problem. Yes, it's me.
yeah, now,
Okay. Skip.
skip those verification. Then you are there.
Yeah. But
Just want you to show that you are not a robot.
yeah, but what if somebody wants to see it that doesn't have a YouTube
I
account?
don't know. I don't know whether if I check on my phone like that, I think I should be able to watch it.
No, anybody that wants to
On
log
your
in,
phone, you
put
can.
in your email and you sign into your.
Okay, let's see what we have here. We're gonna drill, get a kick, just like you guys know, you have already done it, okay? But you are circulating at 100 RPMs. Sorry, you are circulating at 100 strokes per minute, then you are rotating at 60 RPMs, then you are adding weight on the beat. I'm doing it fast because we know how to do it now. I'm speeding it up. And you know where is the problematic formation is starting from here. This is where you get the kick. And in the project, I want you to be able to drill from here to here. Drill through that problematic section to get all the points, obviously. Doesn't mean you're gonna get all the points if you just drill through. You need to do good job on your report and everything. Okay, I'm about to get to the point where I receive a kick. I'm drilling. This is much longer than what it really takes, but now I start getting a kick. You see the yellow stuff here. I pretend I didn't see it just to get more. Okay, you see now I have more flow out than flow in. Now I know for sure I have a kick, but I need to make sure. So I look at that, I'm lifting it up. Okay. And now this will go to 0, but this won't. Flow in will go to 0, flow out won't. And therefore, I'm gonna have, okay, you see the yellow part there. That is a kick. Okay, 138. And now what I'm doing is that, 1 second, let me remove the lines. This is going very fast. I will basically go to the BOP tab, and this is a, sorry. What did I do? No. No, I want to go back, yeah, where I was. And then, okay, what I was trying to show you is what I did with the BOP. No, there you go. So this is an onshore case. So I have an upper pipe ram, I have a choke, and I have a key. And what I need to do is that now I'm drilling. I need to enable, close the pipe ram, and then enable, and then open the choke. you're not really opening the choke. You should say choke line, really. You're opening the choke line. You are enabling the fluid to move to the choke line. And then you need to go separately and close the choke. Because the choke by default is half open. Okay, so I'm explaining because I was gonna do it fast here. Okay, enable, close, wait a little bit, and then enable again and open. Okay, now I will go to the choke. I press here at the choke. Okay, now what am I gonna do? You see, the choke is half open by default. And now the fluid is going there. It's going through the choke line. So I need to hit rig air and then make this 0, right? Because it's like I'm directing the fluid through there, but the door is half open. Okay, let's do that. Okay, okay. Okay, I'm speeding it up to see how the pressure will change. And I'm looking at here and here. Okay, drill pipe, the green drill pipe pressure is now sharing drill pipe pressure, and the choke pressure is now sharing casing pressure. And you see them changing. And this is an old case with a very, very liquidy, gassy liquid, very, very gaseous gas, I guess. The SIDPP will never stabilize, So it was a little bit of a nightmare for the students back then. But that's why I make sure that your kick is bright, so that I made it almost as heavy as I could make it. But still, no matter how heavy I could make it, I can make it 9.6, very heavy, you know?
Yeah.
So anyway, so you see it changing, and you hope that it will stabilize at some point, but it won't. So you need to be looking at a point where the change is becoming more and more steady. It's a little bit more complex scenario. So I go to the tab, the choke tab, and I see here how they are changing. You see, you don't need to know that. You don't need to know that. But you need to get to a point where the change is a little bit constant. And this is what I'm trying to get here. And I think it's going to be around 238, something like that. I'm moving it to see. Okay. And I'm reading from up here. What would it say? I think it's 238 or 243, the max. Okay. So I got that value, and then I will go to my calculator and use basically do what you guys did in part A. If I know my SIDPP, I know what I'm missing. I will add that pressure to the bottom hole pressure and convert that to density. And basically, it will be the FPP, the pressure will be FPP, and the density would be the kill weight max. So I will go to my calculator and make a rough calculation, a quick calculation, not rough. Don't forget to reset to 0. Now we have that. Okay, I guess
to go.
Yeah.
That's how they make their money.
Yeah. You saw that I pressed the reset button?
Yeah.
Don't forget, I always forgot when I was young to press the reset. But you see this where my mouse is? Yeah, reset to go to 0 because you're going to start a new circulation. And supposedly you don't see what's going on down the hole. So, I didn't, yeah. With the driller's method, this is one of the advantages, I need to tell you, I forgot, that you can start the first circulation to get it out without calculating anything. You start it immediately. Okay, so in this case, I will circulate the kick out and then I will calculate the kick mark weight and stuff, although I know already how to do it. Okay, so now I do what I was telling you guys to do. Yesterday it was step 9 or something. You start increasing the speed, start pumping, and then opening the choke. Open the choke a bit more, pump more, until this becomes 40. This here at the bottom, that says 11, is the same as the strokes per minute. Is the pump, is the circulation rate. It's the same as from the first screen. Okay? So you want to get this to 40 by slowly you open the choke a little bit, you increase this. You open it more, you increase that. You play a little bit like that. And this is what I'm doing here. Go, okay. Okay, and now look at this pump speed, the stroke 2.7, pump speed 5, 5.4, 11, 8.1, and I play like this. I do it fast here, but you guys have to do it slowly. And make sure that this is at speed 1 when you do that. Otherwise, it's gonna count it that you're doing that 15 times slower and do a bigger damage. So now I'm at 40 SPMs, which is my designated slow pump rate. And now you see the kick moving up, right? I'm circulating up. Okay. Now I know this scenario pretty well, so I don't really need to manipulate the choke too much. But in your case, you guys need to start playing with the choke a little bit. So it's moving out. Moving out of the yeah, now you look at the casing pressure with the red. As it's changing, it's moving up, right? It's moving up. Also, notice that the yellow column becomes taller and taller as you are moving up, right? Okay. Moving. And you're circulating at 40, SIDPP, SICP, and the flow out here is more than the flow in because the gas is expanding. And it's gas. It's gas. You see, it gets taller and taller. And then yeah, going up. You need to be looking at the pressures at that point. You know the MAASP mask, and you know you should not exceed it. Now, if we turn the sound on, look at that, listen to this. Now it's coming out. Okay? Yeah. Now it's been flared, basically. And in real life, I don't know how much kick I have. Okay, now it's gone. I don't know in real life how much kick I have and anything. So now, if I did it right, those two values, choke and drip pipe pressure, should be equal and positive at the initial SIDPP. So I do the opposite now. I close the choke and I stop pumping. Now, you need to be careful the way you do it so that you don't leave any pressure, any back pressure. Okay? And I think I didn't do it correctly exactly. You need to close the choke last. But I speed it up, and you see they're the same value. The two of them are the same value. And okay, but it's very, very high value. it's a unrealistically high value because of the basically the way the kick was. So I'm gonna go to the calculator and I will use the original value I had, the 238 or something. Okay, I measure the BHP, I add 238 to it. Yeah, 238. Okay, equal, this is my FPP. Convert that to density. This is my density, 10.75. I go back to the app and then I will go to basically change the math. Okay, I go to new math, enable, I will put 10.8. I will put 10.8, I choose green, set, and then I go back, and I do the same thing. I open the choke, I reset to 0. Okay, I reset to 0. I open the choke and I start pumping. I open the choke, I pump more. I open the choke, I do that. You need to be very, very smooth doing that. Okay, very, very smooth. And also have it at ×1, not speed it up when you do that. Okay, now you are reaching 40 again, and you speed up because, yeah, and then we are gonna see the green mud coming in. Okay, now it's coming in, and you have old mud and new mud. You no longer have gas in the hole, so these two are equal and correct. This is good. This is how it should be. Okay, those values that we had before, the 735 at the shut-in pressures, was unrealistic. It should have been 238 on each side, but it was back then when the app had some glitches. With your example, it should be easier. Now, and you already know the values, I gave them to you. So, okay, I'm sending the green mat down hole. And then notice how the pressures are going down as you put the mat inside, because the mat is correct. It's the correct mat way. Now it's coming up, the annulus. Okay, all right, going up. By the way, the app had another glitch. It says 9.6, it should be 10.8. I don't know if your update is better now, but there was a lot of issues that had to be corrected. And every time Windows has an update, the app falls behind a little bit. But it's still good, does the job, you know? Okay, we're coming up. You want to fill the hole well with green mud, and then we're gonna go back and start drilling this section. Okay. And also, why do we count strokes? Because in real life, you cannot see what goes on down the hole. And you don't really know. You may have 2 kick columns, right? You may need to do 10 circulations to make sure that you are out. It's not necessarily, it's not as simple as that, you know? Kick, well-controlled situations, they take days to resolve, to make sure you have everything out, etc., etc. Anyway, keep going, keep pumping, I guess. And this is the default case of the, I don't know if it's the default, I think it's the default case scenario of the app. So if you open the app and you go to surface stats, this is the case that you're gonna get. So you may want to repeat this video. That's a screenshot I took, I guess. You see, this is a 2-hour simulation. Wow. But it was sped up. So when I say it's yours is 8 hours, it's not really that crazy. It's not like 8 hours of yours. Like this is an 18-minute video. So don't worry about that part. but it's longer than this. It's an offshore well. You need to do more stuff. I guess it's gonna take you guys like an hour and a half or something. When you know how to do it.
You don't know.
Hey,
You don't know.
okay, try
Then
it.
it takes a lot of time. So you do.
You do it, then you crash and you go start again.
Yeah, but that's how you learn.
Yeah.
Okay, now you have the well almost filled with new mud. And what you will do is now, if you stop pumping, even if the choke is open, half open, or closed, you will have 0, 0 if you did it right. Okay? So I just stop pumping now, and I have it 0, 0. Look at that. Now I will go here and get to 0 and wait. Okay, I close the choke a little bit. Now, if you close the choke, sometimes you get a pressure on the end of the choke. And that leads to a false reading. That's why you need to be doing it properly. You close the choke first, or you open the choke first when you open the choke, and you close the choke first before starting to pump. I think the app was too sensitive on those stuff back then. Okay, you leave it now. I sped it up. Eventually, both those pressures will go to 0. Huh? Yeah, I mean, okay. I sped it up, and this 600 PSIs, whatever, it will eventually become 0. Okay, and to show you guys, I'm opening the choke to half point as it was before, and I speed it up. You see, it goes to 0 very quickly, and well, not that quickly, but you see 0, 0. I know I'm good. I know I killed the well. And now I will do the same thing as before. Okay, I will go the other way. The well is safe now. I know the well is safe. So I will go to the BOP, enable, close the choke line, enable, open the pipe run, and I'm open back to drilling as normal. So I will go start pumping. Well, reset the stroke counter. Click reset. Oh, I'm showing you that all is 0. Close the, reset to 0. Everything is good now. Everything is 0. Lower the beat. Start pumping to 100 as normal. Now the well is open, right? The well is open. It's all good. Start pumping to 100. Rotate to 60. Okay, add weight on the beat. What did we need? 25, 20, 25 kips. Auto driller. Yeah. And now you want to drill that section that you had problems with. That high pressure section I indicated with yellow from all the way here. This is what you need to drill at your project as well.
A quick question.
Yeah.
Does it mean that after we drill the problematic section, we have to go back to our original mode? Because the new mode will fracture other formation.
No, how do you know the pressure of the other formation underneath?
We don't know.
Yeah. You may have to reduce the mass, but doesn't mean that you have to
go back.
Yeah. So do we have a kick now? Not really, because this is equal to this. Drilling rate is okay. Everything looks okay. I don't think I have a kick now, right? So I drill through the section, and I think I will stop, and I will check if everything goes back to 0. And I will know that everything goes back to 0. Look now, I'm gonna stop. Okay, lift the bit of the bottom, stop rotating, and then stop pumping, and then everything should go back to 0 again. It basically shows me that I did it correctly. Excellent. Okay. So, any questions? on the driller's method as operation wise? No questions? Okay. Okay. Now, those lines that you saw being modeled, how the pressures will vary, are important because this is what we learn in class. And this is what you guys are gonna do in the homework. How will the pressures vary throughout this circulation? Before that, we're gonna see some stuff like, you know why you need to open and close the choke to maintain the drill pipe pressure at a certain level?
The pressure transient of the mud, the choke will tell you kind of instantaneously what you're doing to it. Where if you waited for the drill pipe pressure, you'd have to wait the 1 second for 1,000 feet.
There is some lag time involved in the response. And it's a good point, Justin, you are making, because the app has an option to turn lag time on. I don't remember how you do it necessarily. Let me check. If you go to well configuration or something, but somewhere, I don't remember where, there was a lag time that you could turn on. Because I remember when I was reading an article that the creator of the app made, he said that we turn the lag time off for didactic purposes, for teaching, basically so that things go fast. But yeah, there would be some lag time involved. So don't, in real life, don't move the choke too fast, wait to see the response, make sure the response is proper, and then open it more or close it more. Yeah, that's a very good point, actually. So, any other questions? Okay. So, I'm gonna expect the initial circulating pressure to be that stabilized SIDPP value plus delta PX, okay? Delta PX you measure before you started drilling, right? When you are doing the testing from the first video. And we said it was something like, I don't remember now, it was in the 400s for this default scenario, but for your project, I think it's in the 800s, 850 or something. It's an estimate. The final circulating pressure is very much an estimate. Okay, you don't know it because you don't know when you start drilling that you are gonna get a kick, and then what would be the kill mud weight for that. So you need to approximate that, and you are gonna do like delta px times rho kmw divided by rho mat. Okay, that's complete approximation, but it's acceptable in real life. Okay, that's the best we can do. Okay, we can use other models and estimate that, but I think this is back of the envelope. It's a very, very good. It's good. It's good. Okay. The choke pressure must always be smaller than mass, otherwise you get a underground blowout. For the first circulation, the mass is that. Actually, this is wrong. I have a mistake here. For both circulations, the mass is the same. Because you won't have, this is the mass at the, maybe I didn't put it correctly, end of second circulation is the mass like this, rho kmw. But throughout the second circulation, until you have, okay, yeah, that's the end of second circulation, yeah, that's, but until you get to the point where you fill the entire well, the entire annulus above the casing shoe all the way up to the surface with kill mud weight, you should use the first circulation mass. I should reword that to make it more proper. This is the end of second circulation. And until you make it to the end, you have this value. I will only worry about this when I'm doing any of the two circulations. So only this. Worry about this. I don't know how I didn't catch it 3 years now, or 2 years. Anyway, so how do I expect the pressure to vary? Okay, this is an important plot, a very important plot. This is what I want you to get through the app when you do the simulation and put it on your report. This is what we expect, and this is what we got. Right? We expected this, we got this. Not the same, good enough, similar enough, etc., etc. So I'm starting.
We get the one will be from the app, while we plus one, right? Then we compare. Is that what you're saying?
No, you make a sketch of your own that you expect to see. What do you expect to see based on what you know?
Okay.
Because you are a well-controlled engineer who went to the rig. This is what I'm expecting to get. And this is what I actually got. Okay, why do you think is it different? Maybe the kick fluid wasn't behaving the same way as I thought it would be behaving. Something out of the ordinary. Did you make a little bit of a mistake? Or because you are opening and closing the choke, it was shown there on the plot. I mean, I don't expect them to be the same. But I want you to know what was the difference. You did this here, you did this, you did that. Anyway, so as I'm starting to, I close the well. Okay, I got a kick, I close the well. I'm expecting the SIDPP to increase and stabilize here, right? If I'm lucky, and it's stabilized. You understand that part? SIDPP went up and stabilized, and then I'm starting to pump. When I start to pump, what do I have? Fluid movement. So I have fluid friction. I need to add delta px to that value. Okay? I'm adding delta px. This is a delta px. The gap here is delta px. Okay. Now I'm circulating the kick out. So during that time, steady at that point, I'm just getting the kick out. But the kick may be expanding. So this may be changing a little bit. So even though you thought it would be the same, you may get like going up or going down. You may have, ideally it will stay the same, okay? It may not. If it does, then you need to tell me why. Why do you think is the same case? And now I have the kick out of the well. Oh, sorry, the kick is touching the top of the well there. The choke, and then it's going down. Okay, kick circulated. There is the kick left the well completely, and now I put the new mat, the green mat, inside the well. Okay, I'm pumping green mat inside the drill string. So the green mat is heavier than the original mat. So we said what pressure the mat is missing from controlling the FPP is the SIDPP. Now I'm pumping in new mat, which is the correct density. So that amount that I'm missing becomes less and less and less. That's why I'm going down. Okay? I'm going down, and then I'm steady because I'm circulating mat only on the annulus now. I'm going down until I pump mat inside the drill string, and then I stay steady once it goes up the annulus. Okay? And that steady value is what we call the FCP. That's basically, it would be 0 if I was not circulating. Okay? And this blue line, the entire line, is the drill pipes. Okay? How does the casing side you think is going to look like? I start here at SICP. Why SICP is bigger than SIDPP?
There's a kick there.
Yeah, what kind of kick?
Gas.
Gas kick, which is less than the density of the mud. What if it was the other way around? Is it impossible to have a kick that is SICP smaller than the SIDPP? Oh, it is possible.
This was.
Yeah.
That means
But that's not
higher-
saying it's possible.
higher density.
It's a heavier density.
Yes.
It's a heavier density fluid. I can be drilling with 8 ppg mud, but the actual fluid density of the kick is 8.5. Remember, the fluid density, the actual fluid density is completely unrelated to the FPP. You can have gas low density at a very high pressure. You can have brine very low, very high density at extremely low pressure. FPP, kill mud weight, and the other one, kill mud weight and kick. Rock kick is very, very different. Remember, in the part A, you found 11.3 ppg for kill mud weight, 8.77 for fluid density. Because it was brine. What if it was gas, methane, or something? It would be like 2. Then the SICP would be much higher, even, etc., etc. Anyway, so SICP is supposed to stabilize also, and then it's gonna go up. Okay, why is this going like this? That's because as the kick is moving up the annulus, it gets taller and taller, and then also it's moving up the annulus as well. So remember those equations with square root that we saw? This is basically what they are modeling. And this is what you have to draw for the homework. This part. And there is some gap pointing down here because you go from the drill collapse into the drill pipe, some small deviations there. Okay, so at that peak here, that's the SICP maximized. Then when the kick top is at the surface, touching the choke. Okay, so that's the maximum. And then I'm flaring it out. That's when I hear the shh, because it's being flared out, circulated out. And then I'm done with the first circulation. And then I am pumping kill mud weight down the drill string. Nothing changes in the annulus, stays the same. And then I'm pumping mud in the how do you call it, the annulus. And eventually, once I have the whole well filled I have the whole well filled with green, new mud, kill mud weight. I have 0 on the casing, and I have FCP on the drill pipe side. Do you understand this plot? I know it's complicated. If you go to your app and you click, go to your app and click control methods, and you have 2 plots, driller's method and weight method. If you click driller's method, this is basically what you see. More complicated version of this. Yeah, there you go. So you may have a little bit of waving when you play with the choke. You may have this a little bit moving, some other stuff, but this is the ideal version. If it's excellent, if you do your job, if nature behaves excellently, this is what you are gonna get. It doesn't have to do with the way you do your job. the way you do your job, if you do your job well, you're going to be able to drill through that section that we try to drill, right? That we have the kick section, or we have a problem with. All right. Any questions? Okay. So, what are the advantages of the driller's method? We already mentioned one. Is that you can proceed with the first circulation immediately after the shut-in without waiting the pressures to stabilize. There is no wait time. I did wait for the pressure to stabilize a little bit because it was a very crazy case that we saw on YouTube. But hypothetically, theoretically, I guess, driller's method, you can start immediately. You don't need to wait for anything. You start the circulation immediately. No need for calculations before starting. You can start first circulation by keeping SICP constant until the pump pressure is set. Okay, that's very, very good advantage that you have. Also, the pump pressure is easier to control. Now, this has to do with the you have only two densities in the system. Okay, you have the mat, the old mat, and the new mat for the first circulation. Then second circulation is a little bit more complex, but by that time the kick is out. That's the idea. You only have up to two different densities every time, whereas the other method will have three, but it has other advantages. Disadvantages. Requires two circulations, therefore it needs more time. The pressures get higher, so you are more close to that limit of mass than before. Yeah, there is some, you need more mat volume in general, because you are going to do two circulations. And offshore, they really don't like using driller's method unless they are forced to. Main limitations of the driller's method that I want you to know is not recommended with subsea wellheads, dangers of lost mat returns, where only surface casing has been set, where there are badly worn spots in long casing strings, when the BOP staggered and surface casing configurations make the wellhead flange a critical point, horizontal wells, etc., etc. Basically, these limitations are all related to the fact that the pressures are going to be higher. Okay, if the pressures are higher, I'm closer to mass than with other methods. That's why I don't want to use that method there. Doesn't mean I cannot use it. It's not recommended, but like I said, the experience of the crew is what matters. If they are very familiar with the driller's method and this is what they want to use, I will use that. All said limits have to do with the fact that the heavier kill mat weight is not pumped in the well until the second circulation when the kick is out of the hole. This enhances the pressures of the annulus, and along with that, the likelihood of lost circulation, fracturing. Fracturing is basically underground blowout. Anyway. Are they waiting? Oh, okay. In subsea wellheads, the riser choke line can hold back pressure, which can also trigger lost returns. That means you can have pressure on the choke side, additional SICP pressure, and then that can make your situation even worse. You need to be very careful with this stuff. Okay. Gas migration and expansion. We'll finish that next lecture, but I just want to introduce it. Okay, because you already know about it. You know that as the gas is moving up, it expands, 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 expands. And that can be cause of very big headaches, okay? And detail easy to overlook that can cause a lot of confusion. gas bubbles float or migrate up the hole because of their density difference with the mass, like a helium balloon. If I have a helium balloon here, I believe it's going to touch the ceiling, right? Okay, same thing with the gas. The thing is that as the gas is moving up, SICP is increasing, you get closer to mass. Once you hit mass, you have underground blow. If there is some salt water mixed with gas, the mud may thicken enough to prevent gas rising. That has to do with chemical reactions. As gas bubbles rise, they expand. And if not allowed to expand, they bring pressure from downhole up with them, causing an increase in SIDPP and SICP. Now, you don't control what kind of fluid enters your well, okay? So you may be dealing with a gas, and you may be sitting there waiting for pressures to stabilize, and they are not stabilizing, just like the example in the app. Okay, and you sit there, you see the pressure increasing. If you see, that's why you need to know mass. If you see the SICP approaching mass, you need to open the choke a little and release it, regardless if you are circulating or not. Okay, this is why you do that. Now, that example in the app back then, if you let it like this, the gas will hit the top and the pressure will be somewhere around 700 on the casing side, SICP. In that case, you need to, if the mass is 500, you are in trouble, because by the time it becomes, it will overcome the 500, and then you have from the 238, and then you will have trouble. But if it's like something like 900, then you're okay. But you need to be monitoring the pressures all the time and understand what they are trying to tell you. Simple solution, what I just said. Bleed off pressure by releasing some mud through the choke so that SIDPP is kept constant, and hence BHP is also kept constant. SICP will keep rising, and this is SICP, this is what you need to be comparing with mass all the time. It needs to stay always, maybe I should keep this sentence and say, and stay below mass all the times. Never should you have SICP bigger than mass. Okay. Are they waiting?
As of now.
I was like, if I can do, I will just show you the steps that are different for the weight and weight method, and then we're gonna finish. Okay. Now, weight and weight method, or the engineer's method, is a little bit of a more sophisticated or seemingly more sophisticated method. You're gonna try to do everything that you did with one circulation.
Wow.
Only one. Okay, so you're gonna start from the kill mud weight. So you're gonna wait for the pressures to stabilize like you did in the part A of the project. Get the KMW, which is for you, it was 11.3. And then you will start pumping from green. Okay, so you're gonna try to do it at one circulation. I think you understand the advantage of that. Now the difference would be step 9 of the process would be DM's step 11 would be changing the mud weight. That enable new mud weight, choose the color, set that step. Step number 10 is DM's step number 9. Reset stroke, slowly open choke, and increase pump rate to 40 SPM in small successive increments. Notice that you first open the choke, and then you increase pumping. You need to go like this. Increase choke, increase pumping. I think in the video, the first time I did it wrong. I just noticed it. I just noticed it today, I mean. Step number 11, you use DM's step number 13. DM is driller method. Once the entire mud column has been replaced with kill mud weight, decrease the pump rate to 0, in small successive increments. And then step number 12 is DM's step 14. Close the choke line and open the upper pipe run. Basically, open the well back to normal drilling operation. And finally, step 13 is DM's step 15. Lower the bed and resume drilling activity. Now, you see, we only have 13 steps. With DM, we have 15 steps. There is a reason for that. We only use one circulation. I mean, there's an advantage associated with that. Now, 2 steps less is a lot of hours drilling time. You save a lot of money if you do it properly with weight and weight method. And we're gonna go through that more detail next week. Anyway, now I need to log out of a bunch of stuff. Thank you very much.
Yes, sir.
I will see you. I will extend the homework until Wednesday, probably. Thank you, Donald.
Thank you.
So I did sign out. I don't know if I didn't. So now it's not me, basically, in the. Yeah. I don't care if I leave Blackboard on. I don't want to leave other stuff on. Okay. Let me stop recording.